happen? Well, you can't answer these questions on an empty stomach. Turns out that by looking at my breakfast, coffee and a donut, we can get a pretty good sense of what string theory says about whether the fabric of space can tear. Imagine that space is shaped like this donut. You might think that it would be very different from a region of space shaped like this coffee cup. But there's a precise sense in which the shape of the donut and the coffee cup are actually the same, just a little disguised. You see, they both have one hole. In the donut, it's in the middle, and in the coffee cup, it's in the handle. That means we can change the donut into the shape of a coffee cup and back again without having to rip or tear the dough at all. Okay, but suppose you want to change the shape of this donut into a very different shape, a shape with no holes. The only way to do that is to tear the donut like this, and then reshape it. Unfortunately, according to Einstein's laws, this is impossible. They say that space can stretch and warp, but it cannot rip. Wormholes might exist somewhere fully formed, but you could not rip space to create a new one over Manhattan or anywhere else. In other words, I can't take a wormhole to work. But now, string theory is giving us a whole new perspective on space, and it's showing us that Einstein wasn't always right. To see how, let's take a much closer look at the spatial fabric. If we could shrink down to about 1/millionth of a billionth of our normal size, we'd enter the world of quantum mechanics. The laws that control how atoms behave. It's the world of light and electricity and everything else that operates at the smallest of scales. Here, the fabric of space is random and chaotic. Rips and tears might be commonplace. But if they were, what would stop a rip in the fabric of space from creating a cosmic catastrophe? Well, this is where the power of strings comes in. Strings calm the chaos. And as a single string dances through space, it sweeps out a tube. The tube can act like a bubble that surrounds the tear, a protective shield with profound implications. Strings actually make it possible for space to rip. Which means that space is far more dynamic and changeable than even Albert Einstein thought. So, does that mean that wormholes are possible? Will I ever be able to take a stroll on Everest? Grab a baguette in Paris? And still make it back to New York in time for my morning meeting? It would be kind of cool, though it's still a very distant possibility. But one thing that is certain is that string theory is already showing us that the universe may be a lot stranger than any of us ever imagined. For example, string theory says we're surrounded by hidden dimensions, mysterious places beyond the familiar three-dimensional space we know.
People who've said that there are extra dimensions of space have been labeled as, crackpots or people who are bananas. I mean, what do you think there are extra dimensions? Well, string theory really predicts it.
What we think of as our universe could just be one small part of something much bigger.
Perhaps we live on a membrane, a three-dimensional membrane that floats inside a higher dimensional space.
There could be entire worlds right next to us, but completely invisible.
These other worlds would, in a very literal sense, be parallel universes. This isn't a particularly exotic or strange notion.
No wonder physics students are lining up to explore the strange world of string theory.
String theory is very active. Things are happening. There are a lot of people doing it. Most of the young kids, given the choice, at a ratio of something like 10 to 1, they will go into string theory.
But strings weren't always this popular. The pioneers of string theory struggled for years, working alone on an idea that nobody else believed in. Here's the gist of it. For decades, physicists believed that the tiniest bits inside an atom were point particles. Flying around the outside were the electrons, and inside were protons and neutrons, which were made up of quarks. But string theory says that what we thought were indivisible particles are actually tiny vibrating strings.
It's nothing really mystical. It's a really tiny string. It either closes into its little circle or it has endpoints, but it's just a little string.
In the 1980s, the idea caught on, and people started jumping on the string bandwagon.
Well, the fact that suddenly all these other people were working in the field had its advantages and its disadvantages. It was wonderful to see how rapidly the subject could develop now because so many people were working on it.
One of the great attractions of strings is their versatility. Just as the strings on a cello can vibrate at different frequencies, making all the individual musical notes, in the same way, the tiny strings of string theory vibrate and dance in different patterns, creating all the fundamental particles of nature. If this view is right, then put them all together and we get the grand and beautiful symphony that is our universe. What's really exciting about this is that it offers an amazing possibility. If we could only master the rhythms of strings, then we'd stand a good chance of explaining all the matter and all the forces of nature, from the tiniest subatomic particles to the galaxies of outer space. This is the potential of string theory, to be a unified theory of everything. But at first sight, in our enthusiasm for this idea, we seem to have gone too far. Because we didn't produce just one string theory, or even two. We somehow managed to come up with 5.
5 different string theories, each competing for the title of the theory of everything.
And if there's going to be the fundamental theory of nature, there ought to be one of them.
I suppose a number of string theorists thought, oh, that's fantastic, that's wonderful, and maybe one of these will end up being the right theory of the world. And yet there must have been a little nagging voice at the back of their head that said, well, why are there 5?